Ready here too.
Hey there.
Hey, everybody.
Howdy. My name's Ronnie here, and the four gents on the Zoom screen with me have spent a good portion of their lives totally involved in this fascinating and expanding science, astrophysics. I'm sort of catching up late in life. We're all members, some of us on the board of SBAU, the Santa Barbara Astronomical Unit, Santa Barbara, California's longtime astronomy and telescope club. Doggone it. This will be the 241st episode of the SBAU Astro Hour, our regular weekly log podcast, Monday mornings, 11. We're into our fifth year. SBAU proudly, I wrote the word down and I scribbled it. Oh, assembles, that's what I said, for their first Friday of the month general meetings, plus our second Saturday star parties at the beautiful Santa Barbara Museum of Natural History. Find out all about us at sbau.org, okay? And if you love astronomy, gang, come and join the club, for crying out loud. Here are the cosmic topics. We're going to talk about, as the moon fills up. We focus on a couple of fascinating comets, C2025. I'll get that right. C2025. Why can't I say that? It's called the Lemon. I'll just call it the Lemon Comet. Interstellar Visitor, 3I Atlas. NASA's got a mission called Psyche. It's on its way to the asteroid Psyche. Early evening is a good time to check out a ball of stars, globular cluster M22. It's up in Sagittarius. There's another icy moon in our solar system. Could have a very deep ocean and maybe life. It's Ariel, and we've got pictures of it and the rings around its host planet, Dave.
Doug.
Or is it Doug? It's not Dave. Well, I'm not going to say Uranus anymore.
Like Dave.
Well, Doug, Dave, never mind. Dip something or other. Our planet had a close call. Speaking of rocks, passing space rock last Tuesday night came as close as ISS in this orbit. My God. And I had a good night's sleep that night. I'm glad nobody told me. This is the week we split the light waves. Particles or waves, as we analyze the famous double slit experiment. Let me introduce you, starting with the man in charge, the man behind the talking points, and he runs the show, and he's our beloved president, Jerry Wilson.
Good morning. Good morning, Joyce. Good morning, Calvin, and good morning, Riley.
And good morning to your lovely wife, Pat Forgy.
And Pat.
I had a nice conversation with her on Friday night at the Big Wild meeting. Chuck McPartland's still here, SBAU Outreach, and in charge of most events. He's married to a Pat, our merchandise manager, also doubling as treasurer and doing a good job in both of them, Pat McPartland. Let's see, Tim Crawford signed in, resident lens and telescope expert, old-time fan of mine when I was on radio.
Yeah.
And you're not in the Tuesday workshop anymore, or you just drop in occasionally?
I drop in occasionally, yes.
Okay. Well, you were there. You don't drop on our general meetings a lot live, but you were there Friday, and we'll talk about it next Saturday on the meeting, I guess.
Didn't want to miss that one, boy. It was really good.
That's right. Alexei Vladimir Filipenko. Jim's married to Crawford. And son of a gun, if Tom Whittemore is not on screen with that beautiful tree behind him. Tom, editor of our newsletter, former Westmont College instructor, and I guess our connection to the third Friday meetings. We go out there, and did you have something over the weekend out there? Were you watching the moon?
It was International Observe the Moon Night.
Yeah. And I missed it, but that's okay. And he's married to Maureen. Well, we do the weekly cartoons to start things out. These are silly science cartoons. Some of them are thought provokers. We got a Calvin and Hobbes and a couple of stupid monkeys in a tree, and God knows what he'll call up first. I've got my notes about him. Here we go. A little levity to start the show. Mount Rushmore, before it was carved, its natural beauty was unprecedented.
Oh, I didn't see that one.
I didn't either. You didn't send this.
That's really good.
Next week's?
I think this was that first one that came that some of us didn't have an attachment.
Yes.
You're going to need to fix this one. It's a little washed out. Is that?
Yeah.
Washed out?
Yeah.
It's not the one that you sent us that showed the.
No, some of the times I change computers and I can't get at some of the things I had before.
Oh, all right. Well, my notes are useless.
Oh, well, surprises are always good.
Yeah.
Yeah. Well, call up anything as long as we can see it and it's on the right format or whatever. Ah, there it is. Can you enlarge it? Let's see. Calvin, Suggen, Hobbes, this Tiger Buddy. I don't think math is a science. I think it's a religion. Scratches his tiger head. What, a religion? Yeah, Calvin says all these equations are like miracles. You take two numbers, and when you add them, they magically become one new number. No one can say how it happens. You either believe it or you don't. He says this whole book is full of things that have to be accepted on faith. It's a religion. And the tiger finally leans in and says, and in the public schools, no less, call a lawyer. Calvin goes, as a math atheist, I should be excused from this. He's right. But it's very right on. Okay, this is the one that are one of those guys supposed to be
Professors.
oh, they're just professors. All right. Nothing. They're sitting under the trees about to be crushed by a huge apple. Nothing yet.
Yeah.
They're asking each other, nothing yet. No, how about you, Newton? That's Isaac's grandson, Fig Newton. And this is a problem. You just got to figure this out on the moon. If you're wearing a spacesuit, your nose itches, you're in deep trouble. You can do is scratch the front of the life insurance being sent out.
This might be a little subtle if you're not a Star Trek fan.
There's not a caption on this. It's out of
He's
sight.
not the captain, but he's wearing a red shirt.
It's Ensign Deadmeat.
Yeah, so he's in all the episodes, if anyone gets killed, it's always the tech with a red shirt on.
Oh, I didn't know that.
Yeah, and a matter of fact, they made another movie made a spoof of that. I forget what the name of the movie was, but it was a bunch of actors that aliens thought were real Star Trek or spaceship commanders. And so they just beamed them all up and said, okay, here's our ship. You're going to face the enemy with us and lead. And one of the guys said, oh, no, I'm the guy in the red shirt.
Yeah.
So they all wore red? I don't recall.
No, only certain grade of technicians in the away team wore red.
Oh, and they all died.
If anyone died, they were it.
Yeah, Ronnie, it's like on an aircraft carrier. You have people wearing different color shirts depending on what their job is. So if you're an armorer, you wear one color. If you're part of the flight direction crew, you wear another color. There's yellow, green, red, really obvious colors so that you can orchestrate it and tell people are doing the right thing in the right place.
But Kirk and Spock and the main guys wore yellow, didn't they?
Or blue for science.
Yeah.
Okay.
I never knew that. Never knew that. You learn something every day.
We certainly do. Here's a couple of, is it a family? Is that a husband?
Yeah, it's a family of rattlesnakes, the mom and the dad.
Oh,
and the little snake is shaking his head, not his tail. So this is your side of the family, you realize.
That's right.
I didn't get that. I didn't get that.
This is all brand new. No, this is from his new computer, I guess. Well, hit us again. Oh, I've seen this one. Took me way too long to realize that this is a shower and not a Dalek.
A Dalek.
Dalek. What is a Dalek?
If you ever watch Doctor Who, the chief bad guy was this one bunch of robots that look just like that called Daleks. And all they do is say the word destroy humans or something, and then they roll around. And
the fourth thing on the screen, it looks like a salt shaker to me.
Whatever. But it's supposed to represent a shower in here.
Okay. All right. We got stuff to talk about, including the slit lights experiment later. But the moon's about to fill. Is it right about now? We're going to get a full moon?
I think it was full last night.
Was it? Behind this cloud cover.
That was clear last night.
Very clear. Yeah, it looks a little shy of full.
So it rolled in early in the morning, huh? Here we are in the sky.
And Saturn was real close to the moon.
Okay, I've lost the share screen here. How do I get it back?
We see it.
You see it, but I don't.
Ah.
Oh,
Try
How did I
clicking
do
at the
that?
top of the, or drag from the top of the screen.
surprise, surprise. You switched computers, Jerry? Why would you do that?
No.
I had that trouble when I tried sharing with this new laptop I got, and I can't remember how I got it back. I ended up doing it though.
If you go, at least on mine, if you go up to the top menu bar, you have meeting and you have Zoom screen, and you can flip between those two.
No, I don't have that.
Hmm.
The
I
top,
thought that I-
the top of the window, not the absolute top of your screen.
Okay, so
Oh,
I've
there
got
you
all
go.
you guys here.
Yeah, so you're in meeting view.
Yeah. Huh.
You got full pictures of us, but you don't have the night sky. What constellation is that?
That's Ursa Major, the big
Ursa
bear.
Major.
The next
Oh,
one
look.
over might say Zoom meeting or Zoom screen.
Well,
And-
anyway, this one, what you're looking at is the finder chart for UGC 5302. It's a galaxy with a let me stop share and then start again.
Mhm.
Yeah, you should be on board with us.
This is a really dim galaxy in a really horrible part of the sky right now.
Yeah, well, can't help that. They find them where they find them.
What were we going to go after? That star cluster?
No, it was a supernova in this galaxy.
Oh,
Okay,
Yeah.
you see the screen here now that the share?
Yeah.
Okay, good. So this is the rough placement of where that thing is near the pointer stars in the Big Dipper.
Hmm.
So this up here, so it's little bit on the way toward the North Pole, the pole star. And this time is about 1 o'clock. So it doesn't show it, but this is rising a little bit here, I think. So it's just up. And let's see, where do we go? This is a photograph, a stock photograph from Pan-STARRS,
Hmm.
of the image of the supernova galaxy. This star that's in the middle is not the supernova. That's a star in our galaxy.
Hmm.
But in this, there is a supernova that is really quite faint. But the astronomy magazine was desperate for things to show at this time when the moon is full. So this is in a different part of the sky than the full moon is. So that's why they picked it way out of the way. So if you have, and this one is such an obscure galaxy that it's not in any of the catalogs on my planetarium software. So I had to dig around for this on a Wikipedia page.
Yeah, that UGC is Uppsala General Catalog, so that's one of the more obscure galaxy catalogs.
Yes. Now this one, this is Comet Lemon, and this is where it currently is. So this is just before dawn tomorrow. I think today's the 6th. Yeah, so tomorrow. This is 5 a.m. So it has just risen a little bit, but it's right on the border between the Big Dipper and Leo Minor, in Leo Minor. And the comet itself, this was a nice picture taken by a amateur.
You should see the one for today. It's up to just under visual magnitude. It's magnitude 6 point something already.
Yeah.
And there's all kinds of stuff going on in the tail.
Okay. Can you get a picture of it up?
Yeah, I can give it a shot. Let's see here.
named after a guy named Lemon?
No,
No.
that's the Mount Lemmon Observatory.
Mount Lemmon near Tucson.
Yeah. And usually the stuff taken from Mount Lemmon is taken by Adam Block.
Mhm.
Is that the one that
Did
just
you study there, Tom?
Yes, I've taken images from the 61 inch.
Oh, okay.
This is a smaller scope that Adam uses, I think.
Okay, I'm there. Let's see. Should I do share screen?
Yes.
Okay, share.
Oh, wow.
Oh, that's very spectacular. You're right.
Yeah.
Who took it?
This was, I think, somebody. Oh, here it is. Okay, from New Mexico
Yeah.
with a robotic scope.
Wow.
So it's brightening rapidly. They're talking now about magnitude 2.9 or 3 eventually.
Wow.
Whoa.
So that'll be a
Yeah.
nice object.
Yeah, but in the morning for us, of course.
Yeah.
How
That's
long are those?
my experience is that comets are usually in the early morning or the deep south.
Yeah.
And by deep, I mean not visible to us.
Yeah.
Tail like that is it long as our astronomical unit? How many millions or
It's quite long. I don't know that I've seen an estimate of it, but a lot of people were having trouble getting the entire tail into the image. Like Jerry's image really shows how long the tail is. This is just a like an active area of it.
Yeah.
But Jerry's image really shows the
but
how
that would
long
be
it
the
is.
that would be the tail that faces totally away from the sun. So
Yeah.
part of the solar wind that causes that, doesn't
And
it?
that's what's causing all those turbulent, details in the tail is a solar wind. And
Well,
also they think there might be rotating active regions on the head of the comet.
Hmm. Yeah, that would give it the detailed structure way back.
last week we talked about three comets, one of them coming around from behind the sun. Is this it?
No, that was the Atlas, one of the other ones.
3i?
No, it wasn't 3I.
3I is the interstellar visitor, right?
Yeah. And that's an Atlas.
Oh,
There
that's
Okay,
was
this
another comet.
this picture was
Swan.
taken by
Comet
an
Swan.
amateur in Crete.
Crete.
And it is taken with a 70 millimeter f6 doublet with a focal reducer to get the wide angle. So this is a very wide angle shot.
But the stuff inside the tail itself of a comet, is it all cometary or comet material, or is some of it the solar wind, the protons that are coming
Well, the
up?
solar wind is not visible to us. This is the stuff blown off the comet and left behind by the comet. Actually, that's incorrect what I said. This is not the path the comet took. This is the path the solar wind goes.
Right. But
So
I
the
heard
comet could be moving this way.
at one point you said their comets have two tails.
It's
Frequently.
an ion tail and a dust tail. Yeah, usually.
And either tail can leave us a nice radiant to pass through and have meteor showers.
No, just the dust tail does that.
Just the dust tail. All right. Amazing.
Tale of two comets.
Well, that interstellar one is going
I
to go
think that
away.
would be two tails of a comet. Oh,
Yeah.
this would be a tail of two comets. Yeah.
Or two tails of two tails.
Yeah.
Charles Dickens astronomy.
Yeah.
That's the tail.
Yeah, all right.
Now, this is another desperate look at getting away from the full moon's glare. This is the summer constellations in the evening sky, but of course, this isn't the summer. We're in fall now, approaching winter. And so this stuff is setting in the southwest. So at 9 o'clock in the early evening, Sagittarius in the center of our galaxy is now about to set. These red dots here are different asteroids, bright asteroids. And this is Pluto up here. If Neil deGrasse Tyson is listening, I haven't got over it yet. So this is the M22 finder chart. And there's M22, a nice globular cluster, very big and very bright, right above the kettle's lid. This is the spout. This is the lid, point of the lid, straight up for M22. We have seen this so many times that I'm not going to show you a picture of it. I don't think anyone has memorized it.
I didn't realize that Nuncle there in the handle of the teapot, the
Nunky.
two, the
No,
two stars actually point to it. So I usually just go up from the lid, but
Yeah.
that's an interesting, I didn't see that. It's almost straight on.
Yeah.
Yeah, so using those two angles, you probably find it easier.
Now, and last Friday's talk by Alex Filipenko, he mentioned a fellow that would check for nova in
Yeah.
extragalactic outside of the Milky Way galaxies, and he did it by memorizing the star patterns
Oh
around
yeah, yeah.
galaxies, and he'd
Robert Evans, I think. Yeah.
yeah, that was very impressive. So unless someone here has memorized the pattern of the different globular clusters, I thought we could get away with not showing another picture of M22.
Well, M4 and M13 both have very distinctive shapes.
Yes, some of them do.
Yeah.
And that also shows that we look at those far too many times,
Yeah.
far too much.
We did one of the best nights I had was up there at Lake San Antonio with Tommy here, and he went from the base of the teapot here right up over the sky and just looking at globulars. He went
Yeah,
all the way up to almost to zenith from the teapot. It was
yeah,
really fabulous.
it was fun. Yeah, and a few weeks ago, I was in the Utah desert. Uh, yeah, Boulder, Utah, basically. And M22 was easily naked eye. And I just took my birding binoculars and moved right through the center of Ophiuchus. And I was picking off globular clusters with my bird binoculars. It was so dark. It was amazing.
Is this the interstellar one we're looking at?
Yes.
Yes, this is the path of
Mm.
Comet 3I Atlas, the third known interstellar object to enter and soon to leave our solar system. And you see it, it's not coming close to well, this is the sun here. It's not coming close. It's coming just within the orbit of Mars, nowhere near the orbit of Earth. We're over here, and even though it might get close to the orbit of Earth, it's not getting Earth.
It's close enough.
Now, if we did have a observatory on Mars, we would have got some good data there. But amazingly enough, we do have observatories on Mars. So
Really?
we have a lot of instruments in orbit around Mars.
Looking down.
What's that?
They're looking down, not up.
Yeah, but you can rotate them.
Yeah, you can do an attitude shift. What do they call that? Anyway, it'll come to me in a minute. But spacecraft orientation is called, line of sight. LOS, line of sight.
Oh.
And it was one of the things that I calculated a lot for satellites when I was working at Santa Barbara Research Center.
Wow.
So
Did I miss something on JUICE? Is the purple one that's coming out from Venus's?
that's JUICE. This
Yeah,
is
what is that?
space probe JUICE.
Oh,
It's on its way to Mars. And
No. Juice is Jupiter Icy Moons Explorer.
Okay, you're right.
This isn't, yeah.
But it's
this
headed
isn't
in the
Psyche
region
either.
of Mars. It's not aimed at Mars, except maybe to get a boost. But you see at these times, November 2025, and it's going to be close to the 3I Atlas. It goes out. This is not to scale, obviously. So these probes, we have probes on Mars, orbiting Mars. We have probes orbiting Earth. We have JUICE on the way to Jupiter. And these things are going to be using their instruments, spectrometers and imagers, to take pictures of 3I. So they're trying to get an accurate read of how big the sucker is, because they really don't know that.
Wow.
We do have observations of its spectra, so we know roughly what's coming off of it.
but it didn't originate from Venus's orbit. It originated from ours, the blue one. So it must have been given a gravitational assist or something.
Yeah.
Yeah.
Got it.
Yeah, they're playing Planet Pinball.
Yeah. Planet Pin. Oh, I like that.
Tilt. How are you gonna tilt? Say goodbye to this sucker, huh?
There's only one Chuck. That's a good one, Chuck. Planet Pinball.
Now, this is a photograph. Actually, it's a series of photographs of Comet 3I Atlas taken from the Gemini South Telescope, which is an 8.2 meter diameter telescope. It's a honking big one. And you can see clearly that they took a series of black and white images taken through different filters. They took 2 pictures through the violet filter. They took 2 pictures through a green filter, and they took 2 pictures through a red filter. And then they stacked them together to get 3 color, what the color, accurate color is for the comet itself in the coma. So this is R, B, and G. So this is what we use on our amateur telescopes with 3 separate filters. We take, and at different times we take the picture, then we stack them together. And here they stacked them all on using the comet nucleus as a registration point.
Now, Jerry, is that an accurate color or a processed color?
That's the $64,000 question of
Okay.
astronomy pictures. And I guess the answer is yes.
Yeah, it could be both.
Yeah, it's an attempt to see the actual color.
That's always a good one. Small, medium, or large? Yes.
Why do you suppose? Explain to me why the comet didn't stack up in colors.
It did, but the colors overlapped, and so you get when you combine the red, green, and blue, you get the actual color, just like on a color television set.
There was a photographer back in the 1880s or 1890s that went on an expedition to Russia, and he had a great big black and white camera at the time, one of these things that takes a picture of the vista, wide angle stuff, and in big negatives. And he took sets of 3 pictures in red, blue, and green filters. And then he came back and he showed the pictures he took, and he projected each of the 3 negatives through red, blue, and green filters. And he lined them up so they were all bore-sighted. And then they showed a true color picture of rural Russia. And he was famous for doing that. I'm sure you can see his stuff. It's really very nice if you look it up on Google.
Interesting. It's interesting.
So that's the similar idea to what we do with our shots here. From the camera on my telescope right now has 5 filter stops on a filter wheel. So I take one with no filter, one with a red, blue, a green, and then an infrared filter.
If I get there tomorrow night, Jerry, I'll have you bring this up again.
Okay, sure.
But now, wouldn't it be fair to say that all the stuff we get from the Mars rovers comes in just black and white, but each one is taken on Mars through a different filter, which they can't really send the color here, and we had the color on our end, right?
No.
All digital cameras do that. Even the ones that appear to take a color picture right out of the camera, they have the color filter, red, blue, and green. They have it deposited right on the pixel. So you have the same filter. It's just not one big filter all at once, but these 3 filters in parallel.
God, how do
Go
they
ahead, Chuck,
do
you were
that?
going to say something?
That's why you lose some resolution with the color digital imager, is because they have pixels that are sensitive to red, green, and blue mixed onto the chip. And then depending on the sensitivity they are to various colors, they may have more of the greens or more of the reds.
Huh.
Then they combine them to give you the color image.
And they can send that complete across.
Yeah.
They send the data, yeah, and we put it together here on Earth. The images are processed here on Earth. They do not do a lot of the philosophy when I was doing this. They send the raw data down to Earth because they don't want the computer that handles all these big data files and does the computation. They don't want it being risked on the spacecraft because it could get hit by some radiation and then you get some defect in the final image. And it
Well,
also takes up a lot of time and effort. Now, there is an interesting effect you've touched on here about human vision. And that is that, like Chuck said, you lose resolution when you dedicate neighboring cells to the same different colors in the same image on different pixels. But if you take in this camera with the filters, if you open it up so there's no filter, then you take a black and white image that gets the full resolution. And that's in our work, that's called a luminance image. And then you process the luminance image for sharpness. And then you add to it later, you add the red, blue, and green image. And it doesn't have to be so accurate. The luminance has to be focused, but the red, green, and blue does not have to be sharply focused, because the human eye assumes color lines up with the resolved image. It's like taking a kid with a crayons in a coloring book where they have the glass line he has to fill in. The kids can't see inside the line. Your eye will put it inside the line. It doesn't have to be accurate. Your eye will go for the sharpest thing, and it will add the colors on top of it. That's why you see all these optical illusions where they have a black and white image, but it fools your eye into seeing different hues of color.
but your web, your $10 billion web operates only in the infrared. How does it get any blues or greens or yellow?
Those are just slightly different wavelengths, Ron. So you could say, okay, the near infrared I'm going to call blue, and the far infrared I'm going to call red, and then you make a color image out of that.
Yeah.
Wow. Wow.
Yeah, but the James Webb does operate in the visible also.
Oh, it does.
Someday it will run, the very long wavelength stuff requires super cold detectors. And someday they will run out of the helium that cools that down. And then the thing will no longer take pictures in the far infrared, but it will still be up there taking pictures.
So Jerry, just to be clear, the luminance is a black and white.
Yes, the luminance is the black and white, no color.
Okay. Okay.
And
the picture that we get from it is an LRBG picture, luminance, red, blue, green.
Okay.
And that's what you're looking at here.
So the Hubble is nothing but an enlarged version of your scopes. I mean, it's regular, right? It's not infrared or.
My camera?
No, the Hubble.
The Hubble uses silicon as the detector, I believe. I don't know how far into the infrared Hubble goes. I think it's just near IR. But even the stuff in the backyard will take pictures a little bit in the infrared, because silicon can see out to almost 1 micron in infrared. And so you have to, if you want a sharp image, if you have a refractor brings like at most three visible color lines to the same focus. But if your camera is sensitive to infrared, then you always have a blur infrared image in the background. And so you have to have an infrared filter. And all your cameras, like Canon and Nikon, they all have an infrared blocking filter in them because of that effect. Their glass lens can't bring all those different colors to the same focus. If you want to take infrared pictures, you have to have your camera operated on and its infrared blocking filter removed.
And cooled down?
No.
Cooling down is not an issue with normal photography.
But that silicone you described, is that in the concave mirror?
No, the silicon is the sensitive element in the chip. Silicon does the conversion of photons to electrons.
Oh, part of the electronics?
Yes, it's the first entry level electronics.
Got it. Thank you.
Yeah, thank you, Jerry. That's neat stuff.
Yeah, we can talk about that tomorrow night too.
Yeah.
No, that we might not. I haven't. Everybody thinks I'm gone in Eugene.
Oh, that's right.
We had pre-canceled tomorrow's meeting.
Oh, okay. We'll do it the following Tuesday.
Yeah. So this is a spectra normalized reflectance at different wavelengths. So it's capturing all the light, and it compares. This is the D-type asteroids, and that is what let's see, 3I Atlas. It doesn't tell me what. So by process of elimination, red here, blue here, green.
Green is 2I. That's Borisov, and 1I is Oumuamua.
Uh-huh.
So
Where's
they're
one? Oh,
comparing the
there's one
different
eye.
interstellar comets here.
Oh, okay.
And the blue and the red are what they're getting for 3I.
Yeah, okay. So it generally acts, the article said, like a D-type asteroid. Nickel, iron, and carbon. The first they were seeing nickel only, and then now they see nickel and iron with a oddball ratio between the two.
Huh. The different colors, what did they mean?
These
There
are
were
comparisons
measurements of asteroids and comets,
Oh,
D-type asteroids and the 3 interstellar comets.
oh, I see. There's 3 different ones there.
You got to keep my hand off that when I sneeze.
4.
Yeah, they're comparing it to known bodies in our solar system.
What's the spike mean on the left, you suppose?
That means it's brighter at 1 micron. This is 10,000 angstroms. Now, you don't normally see angstroms these days. This must be from a Swedish company or something.
But yeah, the green over there, that's 2I. That's Comet Borisov. So it had a lot of emission or reflectance at that wavelength. So that's some element that was in it that isn't in these others.
So this
Really?
is brighter. This is brighter in the infrared, and this one is brighter in the ultraviolet than normal for us.
So the Borisov is on there, but Oumuamua is not.
Oumuamua is the 1I, and that's the kind of reddish brown there, Fitzsimmons. 2I is
Okay, now I
Borisov.
get it.
The
Okay.
yellow one is the D-type asteroids, and the other two, the blue and the brighter red, are this new comet 3I.
Wow. They seem to follow a same path except for that green spike.
They're similar, yeah.
Okay, moving on.
Okay.
More to come. It's a hot topic. As soon as all these other instruments that are out there in space get their data, we'll know more.
This is Uranus.
I must be allergic to 3I.
Hmm.
So this is a James Webb picture of Doug,
Doug or Uranus.
Uranus, and its rings.
Hmm.
This is a picture of, excuse me, I'm going to go blow my nose.
You could mute yourself and nobody'd never know, Mr. Pelican. Huh.
This is showing some of the satellites.
Ariel, isn't that the name of the Disney's Little Mermaid?
Yeah.
So they named the mermaid after whatever.
Well, they're
Shakespearean.
named the moons of Uranus were named after Shakespeare's characters.
Right. And Ariel is Hebrew for lioness.
Okay. Are there a lot of Midsummer Night's Dream characters up there on Moon?
Yes.
Mm.
Yeah, especially Puck.
Puck is one. There you go. I didn't even see it.
In the 1930s black and white version of A Midsummer Night's Dream, who was that guy that always played bad guys in the movie? He was young and he played Puck. James Cagney.
Oh, Cagney played Puck. I
Yeah,
remember Mickey Rooney was the version I remember.
Puck is the Loki of this selection of gods.
So word you certainly don't play with, that's for sure.
So the reason we're looking at this is because someone did a study of Ariel, and because of the convoluted surface here, this was as a probe went by, they've decided that there are craters here, but at least long ago, it was a ice-covered ocean and is now a candidate for, of course, life. This is not a photograph, this is a map of the surface of Ariel. And you see a lot of features that look like cracks that opened up and then fluid came up and froze solid. So it's very much like a suspected to be an ocean. So they've done some examination of it and decided that it is.
Wow.
Now we also have another situation here. This guy passed by us, close, but no cigar. It was about the same height above the earth as that's not to scale as our, because it would be really down here.
Yeah.
Thank you. Okay.
Didn't get bent at all by our gravity?
Yes, it did.
Oh, yeah.
Oh, I see a straight
Not
line.
captured, but bent. This is
Okay.
2024 VT. No, that's a different one. 5 years ago, there was one. This is 2025 TF. Safely passed roughly 250 miles close to our planet on Tuesday, September 30, at 8:49 p.m. Eastern Daylight Time. So, and it was a surprise. It's about, let's see, 230 miles.
They actually didn't detect it until it had gone by, after it had gone by.
Right. It surprised us. It was a drive-by. It's between 3 and 9 feet in diameter. So it's a little rock.
I got a movie of one a couple of days before that, 2025 QD8, that passed like 150,000 miles away. So like 6/10 of the distance to the moon.
Yeah.
Can I share that one?
Yes, please.
All right, let's see if I can
3 to 9 feet. Could
find
have
the
broken
window.
up into lots of smaller. It could have done some damage. It might have made a tsunami if it hit the ocean, wouldn't it?
The 2 foot wide one, not so much damage. It would create a meteor rush of people trying to find the parts of it.
This one was bigger, and I think it's gonna come lower left to upper right. But anyway, let's fire the movie here. The scope wasn't tracking perfectly, so you'll see all the stars kind of move, but then this little thing will come shooting across, and that's the asteroid.
Okay.
There it goes.
Oh, yeah.
Wow.
Lord. Do you know how big that sucker was?
Yeah, I have the size somewhere. This one was bigger. This one was like 300 feet across,
Oh, okay.
and it was going like 40,000 miles an hour.
Jeez.
That would have given us another Tunguska, Russia, wouldn't it?
Yeah, well, that one might have been a little bigger.
40,000 miles an hour relative to us?
Yeah.
Yeah.
Okay.
Well, so much
Or
for
from the asteroid's point of view, the Earth was doing 40,000 miles an hour. And it was
Okay.
standing still.
Fair enough.
Jesus. Well, it's kind of scary if they can come and go with that. Well, it's something that small. If it were bigger, we would have nailed it, you think?
Yeah, I hope so.
Yeah, when they're small, they're less reflective, so they're harder to see.
Got it.
Ronnie, we're doing good. We're getting some physics, we're getting some astrophotography and language from Tommy. We got our professors here.
I know, but you and I are old, Tim, and we'll not remember any of this. But
Of course not. That's what makes it so great. I can see it tomorrow and enjoy it just as much.
Now, if you take light waves and like we do in our telescopes, and it comes in through a circular aperture, and you look under a real steady sky, and you highly magnify the point that represents a star, then you'll actually see a diffraction pattern
Like
from
a bullseye.
because we can't resolve the star, but it looks like a disk, an airy disk surrounded by successively fainter rings. And that's the diffraction pattern for a circular aperture. What we see here this is a diffraction pattern for a linear aperture. That is, it's a single slit. Like you take a piece of aluminum foil and a razor blade and you just cut a slit in it, and then you shine light on it, and you get this pattern of the light as it goes out from the slit. So this is a single slit diffraction pattern, and I'll show you a little bit more about that later.
Yeah.
This, if you do two slits side by side, you get this pattern, which is distinctly different. There's not, and interestingly enough, there's not two, here there's not one line. If you took a slit on a macroscopic scale, say a piece of steel, and it had a slit in it that was like 3 inches wide, and you were using not photons, but you were using bullets, and you were shooting through the steel plate at a target, the pattern of bullets that is possible, it would duplicate the shape of the slit or the aperture on the pattern. It would not show a diffraction pattern. It would just show the square aperture. And then but this is characteristic of waves. The bullets reproducing the aperture is characteristic of particles. So this is characteristic of waves through two parallel slits. Now, this is how waves get from a light source up here, say a pinhole, you get, or a slit, you get light shining out in its circular waves that it travels out, and it goes through two parallel slits. We're looking straight down on the slits. And then each of these slits acts as a source. And so the light now spreads out in circular or spherical circular patterns from this slit and from this slit. And where light overlaps like this, it reinforces the image. So you get a bright spot. If the light is out of phase when it reinforces, you get a dark spot. So you get this pattern from two slits, you get this pattern of light and dark, where the light interferes with itself, depending on the path length it had to go down to get to the place on the screen.
Jerry, can I ask a question now or maybe later?
No, go ahead.
This is so similar to our Ronchi test on
Yes,
mirrors.
it is. But
And
we're looking at an image. We're not looking at a diffraction pattern.
okay.
So, and it's Ronchi, not wonky. But anyway,
Did I say
do the
wonky?
same thing, if we do the same thing, that's with light waves. If we do the same thing with electrons, they're little particles, and they have an electron gun, which used to be in the back of our TV sets. And it fires electrons at the double slit. And when you look at the pattern it makes a pattern that has interference lines in it. So it's acting like waves, not particles. So what you do, oh yes. Now this occurs even if you slow down the rate of emissions of electrons so that you are firing just one electron out there, and then you're looking at the pattern. You can't see just one electron, so you fire individual electrons, say with a minute between them, and then you record the pattern, you get the same diffraction pattern. So that means that one interpretation of that is that the electron is interfering with itself. So the wave nature of the electron is interfering with itself. And that's astounding enough.
Almost as though there were two sources of electrons too.
Yeah.
It's weird.
So anyway, this shows the photons going out as a wave and doing their interference pattern, and they get the interference pattern like this. But now if you set up a photon cell at each slit, so you can watch the electron go through,
Or the photon
go through, then as soon as you do that, you get a particle pattern. That is, the wave nature is gone, and you get particle patterns. That is, it just produces, like they were bullets, it just produces the two slits of the patterns like that. So the interpretation in quantum mechanics of this is that the electron is a wave, a probabilistic wave of where it's going to be. And as soon as you look at it, as soon as it's observed, that probability wave collapses into certainty, and it's where the particle goes. So if you turn this photon detector off, then the wave pattern is recovered. And if you turn it on so that it's being looked at, then it's particle patterns. So
Now, I don't understand why the particle detector um, acts that way. I don't. How do they change that? I know you're both going through the same slit. It's the same photon, but what did they do to change that to get the particle and not the interference the
That's
wave
the
patterns?
thing. That's the weird thing. They observed it. They
yeah,
actually determined which slit it went through, and that collapses everything to where you get the particle pattern. I mean, it's
they
totally
watch it go through. They do it. This works with electrons or photons. So
it's
if you
totally weird.
ask
And if
me,
you turn off the detector, even though the detector is still there,
yeah,
you go back to the wave pattern. So it's not just that the detector somehow is messing with the beam, it's the fact that you recorded where it went. It's
So the,
totally weird, Tim.
I'm sorry. The detector does.
don't be sorry. Your quandary is common quandary. When this was first discovered, you're thinking like everybody thinks.
Well,
It
I'm
doesn't
going,
make sense.
can I be even more basic than Tim? What the heck is a photon detector? Is it a lens?
That's a very good question. No, in
Oh,
order to actually see the particle, you have to interact with it. You have to bounce something off of it. And that's the act of observation. So when you're looking at something, you're receiving information from it, and the information causes the probability density to collapse to certainty.
I like
And so the extreme case
not
of
everybody.
this, extending this, is the moon there when nobody's looking at it?
if a tree falls in the forest and nobody's there to hear it?
Yes, the
Yeah.
answer, according to physics, is there's no noise. If there's nobody there to hear it, there's no noise. If there's nobody there to observe the moon, it doesn't exist. If what was the in 2022, the Nobel Prize was awarded to a pair of physicists for examining the Bell's theorem about this. And they concluded, through experimentation, they concluded that no single particle is real in our universe. The only thing that's real in our universe, there's the relationship between different particles. So there has to be at least two particles interacting for something to be real. And so the photon you bounce off the electron here to make it real and visible is the thing that makes it real. Here, they go through on their own because neither one's real yet.
So you're telling me that there's no Santa Claus?
Yeah.
No, I think actually there is a Santa Claus.
Only if you
Santa
observe
Claus
him.
is an attitude.
But supposedly the whole question was particles or waves? They're both somehow.
Yes, the way to say it, if you set up an experiment and ask nature if an electron is a wave, you will get an answer yes. If you set up an experiment and ask nature if an electron is a particle, you will get yes.
So it's a wavicle.
And that's what we call the wave particle duality.
Well, could you compare it to a flat water surface that is composed of zillions of particles called H2O molecules?
No, that's not a good analogy. Here's a better analogy. You're sitting and in the afternoon, you're sitting by a placid stream and you're fishing. And while you're fishing out there, you've got a net with you to scoop in any fish you might get on the line. And you see this wave moving against the current, and you're thinking, wow, I wonder what that is. So very quickly you grab your net and you scoop out of the water and you scoop it up and it's a fish. Okay, so you cause that water wave to collapse into a fish.
Sounds kind of
That's a
fishy.
wave particle duality.
Sounds kind of fishy.
So there's
Yes.
something behind the scenes that's involved with our reality that we do not understand.
Ronnie, we're doomed.
Yeah.
Well, I'm really trying to grasp this. Can you buy a photon detector somewhere? Does Radio Shack?
Yeah, they're called cameras.
Or eyeballs.
Or
Or
eyes,
eyeballs.
your eyes.
Oh, I see. Anything that it's got to go through it and then through the slit and hit the wall, and it's just wow. Okay.
Good stuff, Jerry.
Yeah,
Was it Niels Bohr that did this back in the beginning of quantum?
say that again.
Who came up with this slit experiment?
Young.
Young,
I
early
forget his first name.
1800s.
Oh, way back then,
Yeah.
before quantum.
Yeah, things have been floating around like this before, and people were very and mightily puzzled.
Right.
Jerry,
And
save
if-
this for 2 weeks from now too, on Tuesday.
Oh, we're going to get into even more stuff next week when we talk about simultaneity.
Oh boy.
Okay, so this is a picture taken by the James Webb. You can see the characteristic diffraction pattern. We know what a diffraction pattern is now. And this is of a star, a young star forming, and it's shooting out these jets in each direction. And it is,
Titari?
what's that?
Is it a Titari?
I think it might be Tari, but it's SH2 284.
Oh, yeah, that one. That's right around the corner.
Yes. This is a nebula that's pushed away by a formation of a massive star that is still in the process of growing. And the speed it's spinning and it's twisting up its magnetic fields. And that's what's creating the acceleration like a rail gun. The magnetic field is driving these particles out along the poles of rotation. And the length and strength of these speed of these things going out is proportional to, let's see, the size of the jets corresponds to the size of the star producing them. Models of that's through modeling the star formation. They make the assumption that it is magnetic fields. They model the magnetic field and they get this pattern. And the strength of that force going out is proportional to the size of the star that's being created, but it's still
a function of mass, Jerry, or
the what?
is it a function of mass?
Yeah, how big the star is. Yeah.
Okay.
The two red parts are the jets, right, going out.
Yeah.
And this is inside our galaxy. It's not a distant.
This is a star forming in our galaxy.
Okay. What's the big star? The 6 points? Is that a?
Well, I don't know. That's just a foreground star in the way.
Oh, I see. Okay.
You know, there's a photobomb in every star.
Yeah.
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 So it's not a nova. Or
No.
is it?
No. This is a star that's just being born.
Yeah.
Oh, is that right? Wow.
Yeah. Ron, I think it's Benny.
Benny?
Benny and the Jets.
Benny and the Jets.
Yeah.
It reminds me of a
that
joke,
first
Jerry.
cartoon up there for you, Tom,
Yeah, thank you.
about the
I like Elton John.
cliff it had been on. Yeah.
Yeah, I think they're redoing This Is Spinal Tap. Did you ever see that?
Oh, yeah. It's a great film.
Big band back in the 1980s, and they're going to do a new one, and Elton John's going to be in it, and so is Paul McCartney.
Yeah.
And what band is it?
It's a one that was created by Meathead of All of the Family. What's his name? Carl Reiner's son.
Oh, Carl Reiner's kid.
Yeah, what's his name?
Rob Reiner.
Rob Reiner.
Rob Reiner.
And he's in it, and he even has a role, and he's the producer and director. I just saw a big thing. Can you remember any of that, Tim?
No, I remember Meathead though.
Meathead,
You
Yeah.
remember what you were
Did you know we
about?
have a company here in town that does moving? That's called Meathead Movers.
Yeah, that's
Yeah.
right.
I
Right.
wonder if that's patterned after him. You know, the Benny reminds me of that joke that I'll share with you. It was like the joke you told in front of the crowd on Friday.
I'm still embarrassed by that. I shouldn't have told that.
It's a good one. I liked it.
Okay.
Yeah, yeah.
I'm
I
a
like
lot more forgiving than most of the crowds.
I like the passage from his dissertation he showed on a screenshot of betting these 4 professors that had to augment his doctorate, that if one of them wants the prize, You remember that? He showed
Yeah.
a little part of his thesis.
Yeah.
The
And not
picture
one
that's-
of the four guys that gave him his doctorate that remembered that or saw it, I guess.
Oh yeah. The little passage inside the yeah, he left
They don't-
a little message in there that you get a free beer or something.
Oh,
Yeah.
that's right, yeah. With
You suppose those things never get
The
fully
Easter
read?
egg.
They just,
No.
the picture I
gentlemen-
remember from that show was the little kid holding something and his face is black and his hair is blown back.
Yeah.
Yeah.
wish we could get that one. Well, I have a feeling we're going to see him again at some point in the future, and we're going to have full
I
time.
wouldn't hold out hope, but it would be very nice.
All right,
I don't think so.
Well, I'll see you all, most of you, I guess, everybody except Tom on the screen Saturday afternoon, and we'll do this again next week. That's all for
Yep.
Astro Hour number 241. Number 242 is coming up, and start party is Saturday night, about 7 or 8. Chuck?
Official start time is 8.
All right.
Setup time 7.
Oh,
Do we have a special way of saying goodbye in this field that we?
Hasta Nebula.
Oh,